Hello everyone. So today we're going to look at some further rules of inference which are necessary if we want to sufficiently prove arguments and prove them with ease and without too much difficulty. So there are many valid arguments, as you would have noticed when we had this class last time, that cannot be proved by merely using the elementary valid forms that we've outlined before. So for example, if you have A and B and you want to get to B from there, so simplification alone will not get you, because A and B, our rule of simplification says A and B therefore A, but it's sort of evident that if A and B therefore A, so A and B therefore B. But if you're going to, how do we get to B? That's the question. So to get to B, we have two options. One is the very uneconomical rule of coming up with two simplification rules, right? But then you come up with 2 or 3 simplification rules, and we can sort of come up with 2 or 3 sort of different kinds of rules. So all rules, we can sort of make many variations of that, but then that would make it very uneconomical for us because we'll have too many rules to learn. So we need actually some additional rules of inference, and these additional rules of inference will help us, not just in this one case, but generally to sort out and to get to sort of, better proofs, to do our proofs much more easily. And for that reason, we have what are called rules of replacement. So these are also rules of inference, but they're not based on these elementary valid forms as we saw last time, but they're based on logically equivalent expressions, right? So what do these rules do? So they permit us to replace a part of a compound statement or the whole compound statement with an expression which is equivalent to the part replaced, right? So that is the idea. It helps us replace a part of a statement with a logically equivalent expression. Now you would remember logical equivalence from when we talked about it last time. So what do we do? What do we have in logical equivalence? So in logical equivalence, we have a sort of relationship between two different propositions which states that their material equivalence, which is the biconditional if you remember, so that their material equivalence is a tautology, right? What does that mean? That means that they always have the same truth value. So two statements are materially equivalent when they are both sort of true or false, right? I mean, that's the idea. Material equivalence is different. So logical equivalence is when they can replace one another. So one statement can replace the another whenever they occur, right? So something like saying that she is capable can be replaced at any point with she is not incapable, right? Or this is essential can be replaced at any point with this is not non-essential. I mean, I'm giving you one example of what is called double negation, for example. We use it it's very intuitive and we use it in language all the time. But the idea is that they can replace one another whenever they occur, right? They are completely replaceable. So what kind of statements make up these logically equivalent expressions, and how many? So we have outlined a set of 10 statements again, right? And these statements will help us form, help us make better sort of proofs, help us do proofs much more easily. So let us look at the first logically equivalent expressions, first set of logically equivalent expressions which form a rule of replacement. So there are two variations of this, and this one is called De Morgan's theorem. We have seen De Morgan's theorems before. So what do De Morgan's theorems sort of do? What do they articulate? So they express interrelations. They're really useful. They express interrelations between conjunction and disjunction and their negations, right? So, and this really helps because, if sometimes you have a conjunction which has been negated and you want a disjunction and the other way around. So it expresses the interrelation between these. So the first variant of this, so the first De Morgan's theorem we can say, or you can call it second, I mean the order doesn't matter, is that of denying a disjunction. So when we deny a disjunction, so for example, when we say it is not the case that P or Q, or if we say, for example, it is not the case that he was incompetent or lazy, right? What are we actually denying? That's a question. Now think of a disjunction. What does a disjunction actually affirm? So if I say P or Q, he was either incompetent or lazy, what I'm saying is that at least one of the two disjuncts is true. Right? So he was either incompetent is true, or he is lazy is true, or both are true, right? So how would we deny a disjunction? So denial of disjunction sort of cannot happen with saying that one of the two disjuncts must be false, because the idea is that any one is true. So right, so if you want to deny a disjunction, you'll need to say that both disjuncts are false. And how do you say both disjuncts are false? You will say he was not incompetent and he was not lazy, right? So not the case that P or Q would be logically equivalent to not the case that P and not the case that Q, right? So that is what a De Morgan's theorem would be. Now another variation of De Morgan's theorem is basically one in which you deny a conjunction. Right? So if you deny a conjunction, now let's think of this. If I say it is not the case that he was both incompetent and lazy, right? So what am I actually saying? Now think of what a conjunction says, P and Q. A conjunction asserts that both P and Q are true, right? So when we deny a conjunction, we don't need to deny sort of that both of them are false. Denying even one of them, saying that even one of them is false will deny the conjunction, right? So what I need to say is that at least one of P or Q is false. So I will say that either he is not incompetent or he is not lazy, right? So for example, our other example earlier of what is called the strong disjunct was he is not both in Delhi and Bhopal. Right? And when we denied it, what did we do? So we denied it by saying that it is not the case. Oh, sorry. When we sort of how did we put it in disjunct form? Forget about denial, right? So he's both in Delhi and Bhopal. To deny it, you would say it is not the case that he's in both Delhi and Bhopal, which is the same as saying he's either not in Delhi or not in Bhopal, right? So that is what denying a conjunction is. Right? So basically what you're saying is that the negation of the conjunction P and Q is logically equivalent to the disjunction of the negations of P and Q, right? And the earlier one was that the negation of the disjunction P and Q is the conjunction of the negations of P and Q. Yeah? And like we did earlier when we were doing truth tables and we were checking for logical equivalences, you can check the logical equivalences, and what you will see is that the material equivalence of these two statements would always be true, i.e. the material equivalence will be a tautology, which is what makes it a logical equivalence. And you can use this method for testing all the logical equivalence that we will discuss in this chapter, right? So now I'm going to talk about a very intuitive, very simple rule which you apply almost automatically when you're doing proofs, but you need to make sure that you apply this rule, right, and not just sort of assume it. For example, when you were doing simplification earlier and you had A and B, and you from that you got B, what you did was you assumed a commutation. So what is a commutation? A commutation is something very, very intuitive. You get it immediately. So the idea is that the order of the elements of a conjunction or a disjunction does not matter. Why does it not matter? Because no matter what order the conjuncts appear in or the disjuncts appear in, the meaning remains the same, right? So if I say P or Q, it means the same as Q or P. And if I say P and Q, it means the same as Q and P, right? So commutation is something that you apply almost automatically, right? But it is extremely, extremely useful. So if you don't want a million simplification rules, or at least two, right, then you want to have commutation as an option. Or if you don't want to have, not just, it doesn't just sort out simplification, because then we could have two simplification rules. But for example, think of something like a disjunctive syllogism, right? So you have P or Q, not Q, right? Therefore P, that's what you want to do. But remember, our disjunctive syllogism says P or Q, not P, therefore Q. So what do? You commute, yeah? So our initial problem, therefore, can be solved fairly easily of simplification, yeah? Another rule, very intuitive, is association. What do we have in association? So in association, we have two rules. These rules allow us to group statements differently. So what do we have in association is basically if you have, for example, P or in a bracket Q or R, you can shift the bracket so that you can get P or Q or R, right? P or Q together, clumped together, and R separately, right? Or with conjunction, if you have P and Q and R, so you can sort of change the brackets. So earlier you had Q and R clumped together. You can clump together P and Q and put R separately in a conjunction. So you get P and Q together and R. Right, so what does association allow us to do? It allows us to move brackets around from here and there, because one thing that you must have noticed, what we have done is that when we express something like a conjunction, like if they're all conjunctions or all disjunctions, it would have been possible for us to not have any brackets between them at all. But we put brackets because that sort of makes it more precise when we are applying, for example, simplification or something, right? So brackets are really important, and this one helps us move brackets around. But do pay attention when you apply association that the relationship between the statements should be the same. That means that they should all be disjuncts when you are using association, or they should all be conjuncts, right? So you cannot sort of, if it's a mixture of conjunction and disjunction and implication and whatever, right, you cannot associate. So you can't shift brackets around, that would just mess up your whole proof. So when you're shifting brackets around, make sure that you can apply association, okay? Right. Now, for a somewhat more complicated sort of statement, but again, intuitive once you get to it, is distribution. So distribution is another rule of replacement and shows two sets of logical equivalent expressions. So what does distribution do? So distribution, as its name sort of explains, it distributes any one statement, let's say P, and exhibits its logical connections with two other statements, let's say Q and R, when it is in conjunction with their disjunctions. So that's the first case of distribution, or in disjunction with their conjunctions. That's the second case of distribution. So to explain properly, so one variation of distribution would be when we have the conjunction of one statement P with the disjunction of two other statements Q or R. So you have P and in brackets Q or R. That would be equivalent to the disjunction, to a disjunction really, whose first disjunct is a conjunction of P with Q, that means with of the first statement with the second statement, and whose second disjunct is a conjunction of P with R, that is the first statement with the third statement, right? So to put it simply, P and Q or R would be equivalent to P and Q or P and R, right? There is another variant to this in which the disjunction, so the distribution works in this way, that the disjunction of the statement P with a conjunction of two others, that is Q and R, so you will have P or Q and R. So earlier you had P and Q or R, this time you have P or Q and R, right? Q and R clumped together, would be equivalent to the conjunction of the disjunction of P and Q, that is first statement with the second statement, and the disjunction of P and R. So that would be the first statement and the third statement. So to put it in one go, so P or Q and R together would be P or Q and P or R, right? Slightly more complex, but I'll just look at the slide and it'll become clearer, right? Once you get used to distribution, it's extremely, extremely useful. So for the next rules, let's sort of recall one of the first rules, the first rule that we talked about, the most intuitive of them all, double negation. It's intuitively clear, as I said, our examples were she is capable is logically equivalent to saying she is not incapable. And this is not non-essential is logically equivalent to saying this is essential. So what we are doing is, I mean, you can think of it as two negations cancelling each other out, or whichever way you want to put it. But basically what it says is that P is logically equivalent to not P, right? So once you get double negation, then a few other rules will be clear, and it is really, really helpful. So one of the rules that is fairly useful to us is transposition. So what happens in transposition is that it permits us to turn a conditional statement around. So if we have P implies Q, we can turn it around to not Q implies not P, right? So how does this happen? Think of it as another, I mean, if you have transposition, you actually don't need modus tollens, and vice versa probably, right? Because it's another way of expressing modus tollens. What does modus tollens say, right? Modus tollens basically says that if any conditional statement, so let's say P implies Q, is true, then if its consequent is false, i.e. not Q, then its antecedent must also be false, not P, right? So we are saying P implies Q, not Q, therefore not P, right? So that whole thing together can be put in a single statement, which basically says that P implies Q is logically equivalent to not Q implies not P. That is, the negation of its consequent implies a negation of its antecedent, right? Transposition is very useful, and you should also intuitively understand what's going on out here. Now, one more rule that is absolutely useful. What does it do? It helps us to move from an implication to a disjunction, and therefore to a conjunction, right? Is called material implication. Why is it called material implication? Is because it actually formulates a definition of material implication. Now, if you recall the definition of material implication, which we had discussed quite some time back, the definition of material implication states that if P is true, then Q must also be true, right? So you can never have a case where P is true and Q is false, right? So what you're saying in a material implication, just the definition of it, is that it is false that while P is true, Q can be false, right? So what you're stating is it is not the case that, in brackets, P and not Q. What does that mean? Apply De Morgan's, you'll get not P or not Q, that is not P or Q, which means that what we are saying with material implication is that when we say P materially implies Q, what we are saying is either P is false or Q is true, right? So P implies Q means either P is false or Q is true. In fact, this whole idea, material implication, is the rule of logic. You know, the whole argument, if you want to put it, if you want to think about it, like, you know, your whole system of logic can be put in a material implication. So what you can do is, what you can have, all the premises together, you can put them all in conjunction, because remember, all the premises are supposed to be true. So all your premises and all the things, new premises that you derive from the premises that were already given to you, can all be put in a conjunction, and you put them in a bracket together, clump them together, implies the conclusion, right? So any argument takes a form of material implication, right? So the premises together implies the conclusion. But this means that there is one big Achilles heel, right? Everything is an Achilles heel. So if any of the premises is false, because remember, they're all in conjunction, right? So if any of the premises turns out to be false, what will happen is that your whole argument will turn out to be false. And if you think of the whole system of logic as one big argument, right, with a lot of true premises, and from which you're deriving new premises and new conclusions and lots of other things, right? So if you have anything that is false in the system, you know, the whole system will explode. And this is what is called deductive explosion, right? Or the principle of explosion, which in Latin is called ex falso quod libet, sequitur, or ex contradictione quod libet sequitur, which means anything follows from a falsehood or a contradiction. Basically, it says that if a statement is false or contradictory, it implies any statement whatsoever, right? So if you have a statement, like if you have this thing is blue and this thing is not blue, right? And both of the statements are true in your system, you can actually derive anything from that. You know, I'll give you an example if you think about it. If I say this thing is blue and this thing is not blue, simplify, you get this thing is blue. Commute, you get this thing is not blue, right? And then to any of those statements, add anything you want. To that you can add that, you know, all trees are purple and dragons are princesses, and I don't know, whatever statement you want to add, right? And then with disjunctive syllogism, you can derive the truth of that statement, right? Which means that if you have a contradiction in your system, anything can follow. Yeah. So and likewise, a true statement is implied by any statement whatsoever, because all statements are true in your system, right? So if the statement is true, then any other statement which is true in the system should imply that statement. Yeah. So this sort of material implication is the kind of crux of logic. Is what you're doing in logic is a sort of material implication, and this. The principle of explosion is the sort of big nemesis of logic. You know, think of it as the danger that logic is sort of confronted with from time to time. Another useful sort of rule, and this one also derives from the definition, is material equivalence. Now, if you recall the definition of material equivalence, what did it say? It said that two statements are materially equivalent if they have the same truth value, right? Which means that either both are true or both are false. So what does that mean? So what that means is that if I say P is equivalent to Q, P and Q, or that's logically equivalent to P and Q, or not P and not Q. It's sort of, that's the definition of logical equivalence, right? So either both are true or both are false. But I mean, think about it. If both statements are true, then they must materially imply each other, as we just sort of mentioned, right? Likewise, if two statements are false, they also materially imply each other, right? Which is, these two are consequences of the definition of material implication that we just discussed. So for any two statements, P and Q, right, what we can say is, if P is true, then Q is true, and if P is false, then Q is false. That means that, you know, with transposition, what you would get is P is equivalent to Q, is logically equivalent to P implies Q and Q implies P, right? And this is why it is a biconditional. So P is true if Q is true, and only if Q is true, i.e. if and only if. That's a relation in a material equivalence. So these are the two ways to formulate a material equivalence. So last two rules, also very, very useful. One of them is called exportation. So what an exportation does is that it asserts that if a conjunction of two propositions implies a third, so for example, if P and Q implies R, then it is logically equivalent to asserting that if one of the first two, so of P and Q, let's take P because, you know, that's how we go, is true, then the truth of the third R is implied by the truth of the second Q, which means that if you have P and Q together imply R, what you're saying is that P implies, in brackets, Q implies R. right? And be careful with the brackets out here, because messing it around can sort of mess up your argument, really, right? We're not saying P implies Q implies R, but P implies Q implies R, right? I mean, I'll write it down so you know what's going on. And the last rule, you again, extremely intuitive, you know what it is, right? You've used it often, is called tautology. Now, this is not the same tautology as when we were talking about earlier. A tautology is, as a rule of replacement, claims that any statement is logically equivalent to the disjunction of itself with itself. So P is logically equivalent to P or P, right? So this is blue is logically equivalent to this is blue or this is blue, right? I mean, this is obvious, you can check with the truth table if you want. And any statement is logically equivalent to the conjunction of itself with itself. So P is logically equivalent to P and P. So this is blue is logically equivalent to this is blue and this is blue, right? So tautology is extremely obvious and extremely useful. So let's do a summary of the rules of inference. So to summarize, there are two kinds. And you need to be very careful to distinguish these two kinds because their applications are slightly different from each other. Right, so the first kind is those with elementary valid forms, in which you have certain forms of arguments which can be substituted by other more complex arguments that are substitution instance of these forms. So for example, with modus ponens, you have the form P implies Q, P therefore Q, right? And you have a more complex argument, let's say A and B implies it is not the case that C or D implies E or something. And A and B, therefore, it is not the case that C or D implies E. So what you're doing is that you're replacing A and B with P, and you're replacing that whole thing, it is not the case that C or D implies E with Q, and you're using modus ponens, right? Please remember that these elementary valid forms can only be applied to whole lines of proof, right? The other set are logically equivalent expressions. What are logically equivalent expressions? As you know, they are, rules of replacement, which are formed with logically equivalent expressions. These rules allow us to replace a component of one statement by a logically equivalent statement, right? A component which is logically equivalent. So if you have A implies, let's say, not B implies C, so you can replace that not B with B. So you can see that these rules are different from elementary valid forms because they can be applied to whole proposition or used to replace part of a proposition which is logically equivalent to the equivalent statement, right? So you have these rules of replacement which work slightly differently from elementary valid forms, and you need to make sure that you apply them correctly to the correct kind of statement. So you don't apply sort of, elementary valid forms to a part of an argument. That wouldn't make sense, part of a statement, sorry. It needs to be analogous. We talked last time about analogous arguments, so these are analogous arguments. So these rules, they form a complete system for deduction in propositional logic, right? And it's sort of, there is a proof of this completeness as well. So they form a complete system for deduction. However, you would notice, and some of you have already noticed, that they're not the minimum, right? I mean, we could have lesser rules. You know, you did not need to learn all 20 of these rules. You know, some of these, like modus tollens or constructive dilemma or destructive dilemma, they could be sort of, gotten rid of, and you would still be able to do proofs, right? But why do we have these? Because if you reduce them too much, your proofs will just become endlessly long sometimes. So that's a problem. Like we did not want, for the same reason that we did not want two kinds of simplification, and we did not want two kinds of or two kinds of disjunctive syllogism. The opposite of it is that we don't want, so few that, our proofs will become endless. They're also sometimes frustratingly short, right? So, I mean, like the whole system, you have certain things missing. So it would have been so nice if we could have just gone from A and B to B, and we didn't have to use commutation. But it's better to have, a short set of rules which we can remember and we can easily learn and apply, but at the same time not so minimal that we would require extended proofs for even the most basic arguments. So that's the logic we use when we are using these rules of replacement. And now that you have these rules of inference, and now that you have these whole sort of 20 set of rules that we have discussed so far, what you can now do is that you can apply these to do proofs, and we will discuss proofs in the next lesson, and we'll discuss different ways of doing proofs, and this will help you make some very sort of these are actually some very powerful tools for helping you prove the truth of arguments. And these tools will, and as you practice, you will get very good at them, and these tools will help you. And if you think about it, these tools will help you sort of come to sort of conclusions, to make deductions sort of much more quickly and much more easily, and you can apply them to a variety of things in other academic fields and in life.